Welcome to Differential Equations, section 5.2. In this section, we need a little bit from linear algebra just to kind of set the stage of why we're doing what we're doing. So, in linear algebra, let's say I've got two sets. I've got a set here which has an x in it. I've got another set over here which has a y in it. This could be from R3 to R3, could be R2 to R2, could be Rn to Rm. T is a function that goes from one to the other. In linear algebra, we call it a linear transformation. So a linear transformation takes an input x and maps it into y. So t of x equals y. So here x is an input into the linear transformation. Now in linear algebra, we can associate a matrix with that transformation. And so if tx equals y as a function, then if I take a and multiply it by x, I'll get the same output. So one has matrix multiplication and one has an input into our transformation. So here's the question. What x's have the property that they are mapped into scaled multiples of themselves? So here's what I'm saying. T of x, when I put that x in as an input, the output is just a scaled version, a constant times the original. Or if I do it this way with the matrix, a times x, that output is just a scaled multiple of itself. So this constant that's multiplied, we call that the eigenvalue. And the x that has this property that it gets mapped under the transformation into a scalar multiple of itself, that's called the eigenvector. So, in question 1 here, we are given this system of differential equations, and so we're going to form matrix A. So matrix A here is 1, 5, 5, and a 1. Now, if AX equals lambda x, if I bring this to the left, I get AX minus lambda x, which, if you think about this, this is really A minus lambda I multiplied by x equals 0. So when we look for these eigenvalues, we form the matrix A minus lambda I. So we essentially take 1 minus lambda, 1 minus lambda. To find the eigenvectors and eigenvalues, we start by forming that determinant of this matrix. So downward diagonal minus the upper diagonal, so got that. And so if we grind through that term by term, takes a little effort, we get to a quadratic equation that is factorable. And it factors into lambda minus 6 and lambda plus 4. All right. So that gives me my eigenvalues of 6 and minus 4. Those are the scaling factors. What we don't know yet are what are the eigenvectors that go with those particular values. So what do? Well, we're going to figure out what that is. All right, so we plug in lambda 1 is 6. Okay, so I get this matrix. And I'd like to solve when is this thing going to be equal to 0, right? Because here's what we're looking for. Move it over, factor it out. I want to know this matrix times what would give me 0. All right, so when I do that, I get something that looks like the following. So here is a minus 6i. I'm going to row reduce this thing. All right, so I can divide this row by 5 and then add it in here. And here's what happens. So when I see this, what that tells me, because I have a whole row of zeros, is that V2, remember I'm looking for V1 and V2 here, is an arbitrary thing, S. And if that's the case, I get V1 minus V2 is 0, which says V1 equals V2. So that says that my solution is of the form SS, where S is this arbitrary number. And so if I factor it out, I get 1, 1. So what that's telling me is for this eigenvalue, this is the eigenvector that actually goes with it. All right, so then I repeat the process by picking the other eigenvalue of minus 4. So plug it in. Again, we're going to row reduce this, divide this by 5, clean this up, and we get this. So looking at this, I see a row of zeros. V2 is S. That says V1 plus V2 is 0, or V1 is minus V2. But V2 is S, and so what I end up here with is S multiplied by minus 1 and 1. That's what that stuff is telling me. And so the eigenvector is minus 1 and 1. All right, so here's my answer now. So here's my eigenvalue of 6 with its eigenvector. Eigenvalue of minus 4 with its eigenvector. And so the general solution is C1 times the first one plus C2 times the second. And so here is what our basic solution would look like. Now, you can also do this with Wolfram Alpha or Mathematica. You can say, what are the eigenvectors of our original matrix? So you just put in the first row, second row. It tells you what it's doing, and then it gives you the eigenvectors and the eigenvalues. So again, use tools to help you out, check things, make sure you're doing the right way. This was our original system. You can say vector field plot, and it'll give me the vector field plot. It'll also give me the integral curves, showing me what the solutions would be based on my initial conditions at time 0. And so that corresponds, if you look at the graph here, to B. All right. In question 2, we want to do the same thing for this system. We're now given some initial conditions. So my matrix A, 3, 4, 3, 2, form A minus lambda I. Find the determinant of that. All right, so we've got that. Again, a little bit of grinding. It is a quadratic equation. It does factor. And so I get 2 eigenvalues. So I plug them in. All right, plug it in. We're trying to figure out what's going to make this equal to 0. And so when you row reduce, you're going to get to here. All right, that's how we got from there to there, was row reduce, set it equal to 0, as we did previously. Got a whole row of zeros, so V2 is T, and now if you plug that in, you get that V1 is 4/3 T. Okay, so that's what I've got over here. If you factor out the T, it looks like that. But we like our eigenvector to not have fractions, and it's just a scaled multiple anyway on the outside. And so I multiply by 3, and I get that the eigenvector for 6 is 4 and a 3. All right, we now plug in our other eigenvalue of -1. So plug that in. It makes it a plus I, so looks like that. All right, and so let's see. We get to there. We're going to want to set this equal to 0. We row reduce. Got a whole row here of zeros, so V2 is T. Now that says here V1 plus T equals 0, so V1 is minus T. So minus T and T, factor out the T, and I get that V2 is -1 and 1. So you could write it that way. Or remember, it's just a scaled multiple. It could be written the other way. Really makes no difference. It will, make a difference when we solve for initial conditions, but for now, no. So again, I could give it my original matrix A, ask it for what the eigenvectors and values are, and notice it gets exactly what we did, but certainly much faster. All right, so now I'm going to plug in. So here's x1, here's x2. We now use our initial conditions. All right, so that's just a question of plugging in t equals 0. So got a system. I can add them up directly, and I get C1, and I can find C2. And so here is what our answer would look like. If I do a vector field plot, it looks like the following. My initial conditions are at times 0. I'm at 1, 1. And so here is 0, here's 0. Oh, so about 1, 1 is there. So looks like going forward in time, we're going to be moving up in that particular path. So looking at the integral curves there. So again, we are about at 1, 1. So we'll say that's about there, 1, 1. So if you're like if this were a river, then following a piece of something floating in the river, it's going to follow that trajectory. And that looks like D here. All right, so looking at question 3 here, we have 3 equations. Form matrix A. I've got A minus lambda I, which is this 3 by 3 matrix. To find the eigenvalues, I need to find the determinant of this thing and set it equal to 0. I also put it in over here in Wolfram Alpha, and very quickly it'll tell me what they are. So if we grind through this, we've got this 3 by 3 determinant. So I expanded along the first row. So the signs would be plus, minus, plus. So with a lot of grinding, grind, 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 collect up like terms, we finally get to this item. I can factor out a lambda, a minus lambda. Turns out that what's left is factorable, and I find out that my eigenvalues are 0, 25, and 4. But again, a lot of grinding behind the scenes. Now, there are some tricks that work sometimes, and that is if you look at your original matrix A here, if you add up all the rows, it just so happens they add up to 25. And that is one of my eigenvalues, which means the eigenvector would be 1, 1, 1. I also notice that 2 of the rows are exactly the same. So when 2 of the rows in your matrix are exactly the same, one of the eigenvalues is 0. And the other thing to notice is that if I add up the sum of the diagonals here, the sum of the diagonals must add up to the sum of the eigenvalues. So when I add up this side, I've got 9 plus 9, 18, and 11, 29. And I already know 2 eigenvalues, and so the third one is 4. A trick that works sometimes. Is it worth doing? Maybe it gives you some insights. All right, and then so for each of those eigenvalues, you would find the corresponding eigenvectors. And we did that, and so that's what my x of t would look like. And so in our final problem, we've got 2 salt tanks. They're going to give me some information about rate constants, which are R over VI. They're going to give you some initial V1 and V2 gallons in the tanks. They're going to give me R is 30. So you can calculate what K1 and K2 are. I plugged that into the system based upon K1 and K2. That gave me matrix A here. And so for matrix A, I can find the eigenvalues. So A minus lambda I, got that. Find the determinant, set it equal to 0. And I get eigenvalues of minus 3 halves and minus 3. So use the minus 3 halves, plug it into this matrix, set it equal to 0, and then I can row reduce, and I can find out what is the eigenvector for that eigenvalue, which is 1, 1. If I do the same thing, go and take eigenvalue of minus 3, plug it in there, I'm going to get this matrix, and when I row reduce it, it would look like this. That says that the second one is t, first one is 1 equals 0, so I get 0, 1 for that eigenvector, which goes with minus 3. All right, and I did the same thing again using Wolfram Alpha. It gave me them. And just to show you, this does work. So here's A, multiply it by V1. I get 0 minus 3, but that's just minus 3 times V1. So yes, it does get mapped into a multiple of itself. In this way, it'd be pointing in the opposite direction of where it started to, but again, in the same direction, opposite, directly opposite. All right, and if I take A times V2, I get this, but that's just minus 3 halves times 1, 1. All right, so that's what my solution would look like. Plug in what I know about being 0, x1 at 0 and x2 at 0. And so I can solve for C1 and for C2. And so we are there. All right, so the question is, what does this look like? All right, so let's look. And so here I see x1 of t. Here is x2 of t. And what you see from this picture is there is a time between 0 and 1 where we're going to be at the maximum amount of salt in tank 2. So the question is, well, when does that happen? Well, that's going to be a critical point of x2. So form x2 of t, and I want to set this equal to 0. It takes a bit of grinding, factor out the common part. This part is never 0, so the only possibility is that's 0. So this is an exponential equation to solve. And I can find the time when that happens. So the time is 0.46209. And I kept as many decimals as possible. So now I need to plug that time into x2. All right, so if you do that and are really careful, you get 3.75 pounds for the maximum amount of salt that's in there. Another thing you can do is just plug this into Wolfram Alpha and have it calculate it for you, keeping all the accuracy it has, and you'll see you do get 3.75 pounds. All right, so hopefully you enjoyed them stuff on eigenvalues and eigenvectors.